Welcome back to the channel. In this video, we will have a look at the squirrel cage rotor, phase wound rotor, starting of induction motor, and lastly, synchronous machines. Squirrel cage rotor is the most common type of rotor used in induction motors. Its unique name comes from its resemblance to a squirrel cage, a cylindrical structure with conducting bars. These bars are typically made of aluminum or copper and are shorted at both ends by conducting rings. When alternating current flows through the stator windings, it creates a revolving magnetic field that interacts with the rotor bars. The rotor consists of laminated iron cores, with conducting bars embedded along its length. Unlike wound rotors, this design has no external power supply. The rotor bars themselves act as short-circuited loops, inducing current when cutting the magnetic flux produced by the stator. This interaction generates a magnetic field in the rotor, producing the torque required for rotation. The squirrel cage rotor boasts several impressive advantages. Its simple design makes it robust and reliable, while being cost-effective due to the absence of external windings or slip rings. These motors are highly durable, requiring minimal maintenance. The lack of brushes or slip rings ensures efficient operation with low maintenance costs and high mechanical durability. It's an engineering marvel of simplicity and effectiveness. However, the squirrel cage rotor isn't without limitations. Speed control is restricted without additional external devices. The starting torque can be challenging, especially in lower-rated motors. While excellent in many applications, these rotors may struggle in scenarios requiring precise speed manipulation or high initial torque. Engineers must carefully consider these constraints when selecting motor types for specific applications. Now, let's explore the phase wound rotor, also known as a wound rotor. Unlike the squirrel cage design, this rotor features windings placed directly on the rotor. These windings connect to slip rings on the rotor's shaft, which interface with brushes. This unique configuration allows external connections to control the current flowing through the rotor winding, providing more flexibility in motor operation. The phase wound rotor's key feature is its specialized winding system. Coils are wound on the rotor, similar to stator windings in synchronous or induction motors. Slip rings and brushes enable continuous current flow to the rotor windings, with the ability to control current magnitude externally. When the motor operates, the rotating magnetic field induces current in the rotor winding, generating torque through magnetic field interaction. Phase wound rotors offer significant advantages in motor design. Their standout feature is the ability to produce high starting torque by controlling rotor resistance through external connections. Speed control becomes more flexible, and for applications requiring high torque, these rotors can provide superior performance compared to squirrel cage motors. They shine in scenarios demanding precise electrical and mechanical control. Despite their advantages, phase wound rotors come with notable drawbacks. The design is more complex, involving slip rings, rotor windings, and brushes. This complexity translates to higher costs and increased maintenance requirements. The slip rings and brushes experience wear and tear, necessitating periodic maintenance. Additionally, these motors are generally larger and heavier compared to their squirrel cage counterparts. Starting an induction motor presents unique challenges. During startup, motors draw a significantly high current, typically 5 to 7 times the full load current. This inrush current can potentially damage the motor and power supply system. Moreover, motors produce minimal torque at startup, with torque increasing as the motor accelerates. For some applications, achieving higher starting torque becomes crucial. The direct online starting method represents the simplest approach to motor startup. In this method, the motor connects directly to the power supply at full voltage. When started, the stator windings are energized at full line voltage, allowing the motor to draw its full starting current. While providing full starting torque, this method can draw 5 to 7 times the rated current, making it ideal for small to medium-sized motors. Direct online starting offers several compelling advantages. Its simplicity is unmatched, requiring minimal components like a starter switch and overcurrent protection. The method provides full starting torque, which is crucial for applications demanding immediate power. Cost-effectiveness is another key benefit, as it doesn't require additional equipment like transformers or resistors. It's a straightforward solution for many motor starting scenarios. However, direct online starting isn't without its drawbacks. The primary concern is the high inrush current, which can cause significant voltage dips in the power supply system. Frequent starts can lead to motor overheating. This method becomes less suitable for large motors, as the substantial current can stress both the motor and electrical distribution system. Engineers must carefully evaluate the motor's size and application. Enter the star-delta starting method, a sophisticated approach to motor startup. This technique reduces starting current and torque, particularly useful for larger motors. Initially, motor windings are connected in a star configuration, then switched to delta once the motor reaches a certain speed. The star connection reduces voltage across each winding to approximately 58% of full line voltage, effectively cutting the starting current to 1/3 of a direct online start. Let's break down the star-delta starting principle. At startup, each phase winding is connected between a line and neutral in a star configuration. This clever arrangement reduces the voltage across each winding. Once the motor reaches about 70 to 80% of its rated speed, the windings are switched to a delta connection, allowing the motor to run at full voltage. It's a strategic approach to managing motor startup challenges. Star-delta starting brings significant advantages to motor operation. The method dramatically reduces starting current to approximately 1/3 of full-line current, protecting the supply system from voltage dips. It's more cost-effective compared to some alternative starting methods and places less electrical and mechanical stress on the motor. For many industrial applications, this starting method offers an optimal balance of performance and protection. Despite its benefits, star-delta starting has notable limitations. The reduced voltage in the star configuration means reduced starting torque, typically only 1/3 of the rated torque. This makes it unsuitable for applications requiring high starting torque, such as crushers or heavy machinery. Generally, these starters are limited to motors up to 100 HP, with larger motors requiring alternative starting methods. The auto-transformer starting method offers another approach to motor startup. In this technique, the stator connects to the supply through an auto-transformer with multiple tapping points. During startup, the motor receives only a portion of the full voltage, typically around 70% of the rated voltage. This method provides reduced starting current and offers higher starting torque compared to the star-delta method. Soft starters represent an electronic solution to motor starting challenges. This device gradually increases the supply voltage to the motor, allowing for a smooth, controlled start. By managing the voltage ramp-up, soft starters minimize inrush current and protect electrical components from sudden voltage spikes. While more expensive than traditional methods, they offer superior control and protection for motor systems. The variable frequency drive represents a sophisticated starting method. VFDs control both voltage and frequency supplied to the motor, allowing it to start at a low frequency and gradually increase to rated speed. This approach provides precise control over motor speed, torque, and current. It offers efficient power use, energy savings, and a smooth startup with minimal inrush current, though at a higher initial cost. Let's explore synchronous machines. Synchronous machines are a type of alternating current, AC, machines that include both synchronous motors and synchronous generators, also known as alternators. These machines operate at a constant speed synchronized with the frequency of the supply current, making them essential in power generation, industrial drives, and various other applications. The principle of operation of synchronous machines is based on electromagnetic induction. The rotor rotates at the same speed as the rotating magnetic field generated by the stator, known as the synchronous speed. Understanding synchronous speed is crucial. The synchronous speed is calculated using the equation Ns equals 120 times F divided by P. Here, Ns represents the synchronous speed in revolutions per minute, F is the supply frequency in hertz, and P is the number of poles in the machine. This equation allows engineers to precisely determine the rotational speed of synchronous machines based on electrical and mechanical parameters. Synchronous machines operate at a constant speed, which is synchronized with the frequency of the supply current. Synchronous machines come in two primary types. Synchronous generators, or alternators, convert mechanical energy into electrical energy. Commonly found in power plants, these machines use a prime mover like a turbine to generate electricity. Synchronous motors, on the other hand, transform electrical energy into mechanical energy. They excel in applications requiring constant speed, such as precision machinery, compressors, and large pumps. The construction of synchronous machines involves two key components. The stator is the stationary part, featuring windings energized by alternating current that produce a rotating magnetic field. The rotor is the rotating component, which can be either a salient pole rotor with protruding poles or a cylindrical rotor used in high-speed applications. An exciter provides the direct current needed to generate the rotor's magnetic field. Synchronous motors operate by locking the rotor onto the stator's rotating magnetic field. When AC is supplied to the stator, it generates a rotating magnetic field, and the DC-excited rotor synchronizes with this field. These motors offer remarkable advantages: constant speed operation, power factor correction capabilities, and high efficiency. They're particularly valuable in applications demanding precise speed control and grid power optimization. Synchronous motors face some limitations. They require a starting mechanism, like an induction motor starter, to reach synchronous speed before locking onto the rotating magnetic field. The motor's design is also more complex, needing additional equipment for excitation and a sophisticated control system. However, synchronous motors find use in applications like large compressors, pumps, clock mechanisms, power factor correction, and precision equipment requiring exact speed regulation. Synchronous generators, or alternators, are fundamental in power generation. These machines generate alternating current electricity in power plants, converting mechanical energy from turbines or engines into electrical power. Voltage regulation depends on the rotor's speed, excitation level, and generator load. Beyond power plants, these generators serve critical roles in backup power systems for large buildings and industrial facilities, ensuring reliable electricity supply. We have reached the end of this video today. Thank you for watching, and don't forget to like and subscribe for more tutorials on other exciting topics.